Hi, I'm Brad McKay. I'd like to share the results of a meta-analysis my colleagues and I recently conducted that examined the performance learning distinction as it pertains to practicing with a reduced feedback frequency. Augmented feedback research and theory has been integral to the hegemony of the delayed retention test in the modern field of motor learning. For example, in the guidance hypothesis, it was argued that previous research had conflated the temporary effects of feedback on performance with relatively permanent changes in ability. And at the time, augmented feedback research was put on its head. Previous studies had seemed to show that a 100% feedback frequency was optimal, but new studies that measured performance without feedback and after a sufficient delay reported that reduced feedback frequencies were more effective for learning. Many of you would have read Schmidt and Bjork's classic paper on the performance learning distinction, and augmented feedback was a key line of supporting evidence in that perspective. In 2012, Kantak and Winstein posited that time-dependent motor memory processes underpin the phenomenon. Again, augmented feedback research was a critical piece of the narrative, as the authors reviewed studies that manipulated practice or feedback schedules and included both immediate and delayed retention tests. Their review evaluated whether the practice variables had consistent effects at each time point. Here's a partial recreation of the data they collected in their review. The key columns report the immediate retention and delayed retention findings. If the statistical significance of the practice variable was the same at each time point, the effect was deemed consistent, whereas if it differed, it was deemed not consistent. Based on this approach, Kantak and Winstein concluded that 63% of studies showed inconsistent effects. This method is called vote counting, and while many have written about its perils, I'd like to show some simulations that illustrate how far astray this method might have led these authors. I simulated 10,000 experiments under 4 different set of parameters. Each experiment consisted of 2 groups of 15 participants. Each participant contributed data to the immediate and delayed retention tests, so the data were correlated between 0.4 and 0.55 depending on the parameters. If the independent variable had an effect, it was a Cohen's d of 0.5, which is often called a medium effect. Here are some mock figures illustrating the 4 different parameters I simulated. In the first situation, the independent variable increased its effect from immediate to delayed retention. In the second, there was a reversal effect, such that one level of the independent variable was more effective at immediate, but less effective at delayed retention. In the third situation, the independent variable had effects on only the delayed retention test. And in the fourth situation, the effect was consistent across both time points. After simulating each of these situations 10,000 times, I counted how many times the vote counting method would correctly conclude that the variable had inconsistent or consistent effects. Here are the vote counting results. In all 4 waffle plots, the red squares indicate the proportion of times the vote counting method got the consistency wrong. As you can see, judging the consistency of an effect by statistical significance at each time point is a deeply flawed approach, albeit not much different than what one might typically see in a review of literature. Here, we present a better way to evaluate the consistency of a practice variable's effectiveness across time points. The multi-level meta-analytical model is perfect for this type of research question. Well, you might not know it, you're probably already familiar with a multi-level meta-analysis. A standard random effects meta-analysis already has 2 levels. The first level estimates the sampling error of the included studies, while the second level estimates between study heterogeneity. My colleagues and I conducted a 3-level meta-analysis that also estimates the within study heterogeneity. In this case, the difference in effect between immediate and delayed retention time points. The results I'll present shortly are from a larger meta-analysis of motor learning experiments that compared reduced frequencies of feedback to 100% feedback frequencies. The studies were required to include either an immediate or delayed retention test, an objective measure of motor skill performance, use random assignment, and sample from a healthy population. Following an intensive search of 2 databases, forward and backward reference tracing, and a targeted author search, 61 studies were identified for inclusion. We compared the groups based on the outcome measure that matched the feedback that was provided, or otherwise based on an outcome measure priority list. Here's a forest plot of the standardized mean difference estimate and 95% confidence interval from each study at immediate retention. The black polygon at the bottom illustrates the overall effect size estimate and 95% confidence interval, which is not significant. And the air bars represent 95% prediction intervals. Prediction intervals illustrate the range of outcomes we would expect to observe 95% of the time if we sampled a random experiment from the same population of experiments these studies came from. As you can see, the interval basically spans the range of all plausible outcomes. This forest plot of delayed retention results shows a similar pattern. Again, the overall estimate is not significantly different from 0, and the 95% prediction interval encompasses the full range of plausible outcomes. As you might have guessed by now, the difference between immediate and delayed retention was not statistically significant. So, we were unable to support the predicted performance learning distinction with the feedback frequency literature. Our results cannot provide evidence that there is no performance learning distinction in general, as other practice variables have also been suggested to have differential effects on immediate and delayed retention. Our results don't even provide evidence against a performance learning distinction for reduced feedback frequencies. We can't rule out moderate differences in either direction. What our results do show is that despite extensive research that ought to speak to this issue, as a field, we have not generated sufficient evidence to establish time-dependent effects for a variable that has been central to the performance learning distinction hypothesis. You might ask, does this depend on certain moderators? We can't rule that out either. But we did test a suite of potential moderators, including task, skill level, age, frequency of feedback, type of measure, amount of practice, amount of retention delay, and risk of bias in a variety of domains. None of the moderators we tested accounted for a significant amount of heterogeneity in these data. My colleagues and I believe that if we want to develop evidence about the performance learning distinction as it pertains to feedback, our time is better spent organizing multi-lab collaboration efforts that can achieve high statistical power rather than searching for hidden moderators in the extant literature. Thank you very much.